All right, so now this one's going to be a little quicker. If you haven't watched Gas Laws Part 1, you should go do that. This just kind of expands upon that. Not kind of, it does. It expands upon that skill of understanding the relationships between pressure, temperature, and volume. So once again, in these, moles are going to be held constant. So we're going to see how does the pressure, temperature, and volume change from an initial conditions to final conditions. Now the difference between this and the first one, though, is in the first one of these three were held constant. So either the pressure didn't change and these two did, or that didn't change, or the volume didn't change and the pressure and the temperature did. In these problems, so we call them the combined gas law. So we're taking, Charles, Boyles, and Gay-Lussacs law, and we're combining them into one problem where all three will be changing. So now all three properties are going to change, but we still only deal with one at a time. So I'm going to jump right in. Like I said, it goes a little quicker. If you have no idea what I'm talking about, go back and watch that other one on Gas Laws Part 1. All right, so we have to be able to look at the numbers and know what number and unit belongs to which property, though. So liters, so our initial conditions, 8.5 liters. Remember what we said about Celsius? Get rid of that. Add 273 to Celsius to get Kelvin. So 25 plus 273 gives us 298. So the initial temperature is 298 K. And then our initial pressure is 100 kilopascals. What is the volume? 50 again, so add 273. If at 323 K and 50 kilopascals. All right, so now, more complicated, yes, but not that much. So volume equals 8.5 liters. So now, instead of just having one fraction, we're going to have two. That's it. And then we just do each separately. So what we want to check first is, I'll do pressure first. So the pressure is going from 100 to 50. So the pressure is going down. We want to know how is that going to affect the volume. Now, it's probably going to affect the temperature too, but the temperature we know. So we don't have to worry about how it affects the temperature because we know the temperature. We want to know how is it affecting the volume. So the volume will go up. Remember, pressure down, volume goes up. So in order to make the volume go up, we want to put the bigger number on the top. And the kPa and the kPa will cancel. So we just have to make sure those units are the same. So that one's done. So now we took care of the pressure. So now let's see how the temperature affects the volume. The temperature is going up. When the temperature goes up, the volume will also go up. So again, we're ignoring the pressure because we know what the pressure is. So when it went to 323, it went to 50. So we want to know when it went to 323, what happened to the volume. So the volume has to go up. So once again, I'm going to put the larger number on the top. Kelvin and Kelvin are going to cancel again. My unit is going to be in liters. So now to solve this, you could divide that, and divide that. But I like to just go multiply, 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 divide by that, hit equals, divide by that, hit equals. I don't have to write anything down then. I don't even have to have a fancy calculator. You can just keep going. So 8.5 times 100 times 323 divided by 50 divided by 298. So the correct answer is 18.4 liters because the units of liters will be left over after the kPa and the K cancel. All right, so that's it. So if you watch the first video, you can see it's just a continuation of that. We do the pressure ignoring the temperature. We do the temperature ignoring the pressure. And we just have two fractions instead of one. All right, so next one. So again, P, G, and V, initial and final. A gas occupies a volume of 500 milliliters. So volume is 500. 1.25 atm pressure. Get rid of that. 303K, so add 273 and we get 303K. At what pressure will it equal? 750 milliliters, and once again, get rid of that, so 363K. Pressure equals 1.25 atmospheres times our two fractions. The temperature is going from 308 to 363. So the temperature is going up. When the temperature goes up, the pressure will also go up. All right, so I need to put the larger number on the top. Volume is going up. When the volume goes up, the pressure goes down. So this one's going to make the pressure go up. This one's going to make the pressure go down. So I want to put the larger number on the bottom to make it go down. So the temperature is going to make it go up. The change in volume is going to make it go down. One of them is going to win. We'll be able to tell by doing our answer. So 1.25 times 363 times 500 divided by 308 divided by 750. So the correct answer is 0.982 atmospheres for the pressure. There's the correct answer. So you can see the one that affected it more would have been the change in volume because it ended up lower than when it started. So this made it go up. That made it go down. This one affected it more. P, T, and V, initial and final. All right, so the pressure is 715 millimeters of mercury. The temperature is, already in Kelvin, hooray, 5.75 liters. What is the volume of this gas at STP? All right, so there's that phrase, standard temperature and pressure. We learned standard temperature is 273 Kelvin always. Standard pressure, it depends on what unit we want. We could use atmospheres, 1, kPa, 101.3. But this one's in millimeters of mercury, so I'm going to use 760 millimeters of mercury. Standard temperature is 273 Kelvin. So volume equals 5.75 liters times, get rid of my equals there. Pressure is going from 715 to 760. Pressure is going up, so the volume goes down. So I put the larger number on the bottom. Again, millimeters of mercury will cancel. Times, temperature is going up, which should cause the volume to go up. So I want to put the larger number on the top. So one, again, is making it go one way. One's making it go the other way. And I did that with my fraction. So now I have 5.75 times 715 times 273 divided by 760 divided by 200. And I get 7.38 liters as the answer this time for the volume. Next one. P, T, and V. Initial and final. All right, so my initial, it says 2.89 for the liters. Aha, another Kelvin, so 298 K. Standard room temperature, 25. And we have 895 millimeters of mercury. Determine the temperature in degrees C, but remember you have to do Kelvin, change it at the end, that will occupy 4,500 milliliters and 0.850 atmospheres. All right, so now we have a little bit of an issue. You can see that the units are not the same. We have liters and we have milliliters. So we have to make sure they're the same so it can cancel. Same deal here. We have millimeters of mercury and we have atmospheres. So I'm going to change this one to atmospheres. So 895 millimeters of mercury. Remember, we use those standard pressure values, which is 760 millimeters of mercury and 1 atm. So we have 895 divided by 760, and we get 1.18. So this is 1.18 atmospheres. Same deal over here, 1, 2, 3 to the left, and make it liters. That's the easy way to do that one. So milliliters to liters, 3 to the left, or divide by 1,000. All right, so now temperature equals 298 K times our two fractions. The pressure is going from 1.18 to 0.85. So the pressure is going down, which is going to cause the temperature to go down. So bigger number on the bottom. And the volume is going from 2.8. So the volume's going up, which means the temperature is going to go up. And so we put the bigger number on the top. Liters cancels. Atmospheres cancel. Our unit is going to be in Kelvin. So, oops, wrong button. 298 times 0.85 times 4.5 divided by 1.18 divided by 2.8. And I get 345 Kelvin. I want degrees C according to the problem. So negative or minus 273. Minus 273, and I got 72. So 72 degrees C will be the correct answer in Celsius. All right, so now everything that I'm showing you here can be done with a formula. If you looked online, you can see these. I don't use these, but you can see they're there. I cut and paste this out of something I found on the internet. So you can see there is a formula for Boyles' law. There is a formula for Charles' law, Gay-Lussacs law, and then the combined gas law. But then you got to remember these formulas. Or you're given those formulas, which I think is a waste of time, because you don't need them. If you know the relationships, you can solve the problems the way that I have. Instead of trying to remember, all right, P1, V1, P2, where does the ones go, and then this combined sucker here. I don't like it. If you want to memorize those for my class, you can go right ahead and do that. I have no problem with that if you can get the right answer. I just think the way that we do it is easier. All right? Good luck.